Hello, and welcome to Game Revolutions, the series some are calling Antiquated Techniques for Coding an Antiquated Game on Antiquated Hardware. What do they know? They don't know anything. Don't listen to them. In the past few videos, we have been talking about speeding up existing features of our game. Today, we get back to adding brand new features. First, a way to encode a player's progress through a level and when to bring new game elements onto the screen. Second, let's make some holes in the ground. And finally, a game design element that was broken by those holes that we needed to rethink. All that and not more today on Game Revolutions. So first I'm just going to run what I've got so you can see it, and then we'll talk about the code and how it works. You're going to notice there's a few things that are different, but for now just focus on the ground and keep your eye on the right hand side. Oh, there it is! It's a hole! And another hole and another hole! And you'll notice as they scroll on, you'll see a partial hole kind of naturally going on, and then you get partial holes on the end. And so even though the ground is rotating, the holes are clearly not rotating. So these are now coming on when the level decides they're supposed to come on, and then they go off as they naturally scroll to the left. Now there are a couple other things happening. You'll notice I've got some numbers here. This is to keep track of what frame I'm on, and we're going to see a little later why that's going to be useful. And the other thing is you've probably noticed this is going a bit slower. This is so that I can more easily see what's happening, and this is probably a better game playing speed anyway. And actually, why don't we take a look at the code and see what's slowing it down. So here's the main part of the main loop, and these are all the routines that get called. And if we scroll down, you may recall we re-enable the vsync interrupt, and we sync, and then we would disable the vsync and then go back up to the top. But now we've got a sync loop. So rather than waiting for the end of the frame to swap buffers and then return to the top of the loop, we actually wait for 5 v-blanks. So we're waiting for our frame and then 4 more frames. Now I did spend a lot of time trying to get things as fast as possible, so it might seem strange that I'm now throwing that all away, but I'm pretty sure I'm going to have to stop doing this at some point, because the more things I add, the more processing I'm going to need. But for now it's pretty thin and fast, so I need to slow it down just so I can see stuff. Now if you're curious to see just how fast it would be, I could change this to 1, and now we would go back to only doing a single sync. Let's see how fast that would go. Yo! Yo, yo, yo! Yo, yo, yo! Try playing that, man. That's pretty fast. So let's start with the data that controls what happens when. So I've added a new struct here, which represents a single entry in our progress through a level. So each entry has 2 things. They have how many frames it takes until you get to this entry, and then what to do when you get to that entry. And so the data for that is down here. So what you just saw was after 10 frames, we make a hole. After 110 frames, we make a hole. And then just 10 frames later, we make another one. So this is why you saw 2 holes on the screen at once the second time and only 1 hole the first time. And then up at 220, we add a hole, 5 later, another hole, and then what is that, 15, 20, 15 later, another hole. And so on and so on. Right now, the only action we have is to add a hole. So I anticipate there will be more actions to come, like make a rock or send some enemies my way. And because I'm using this number of iterations or this number of frames to tell me when to do the next action, that's why it was useful to show in the upper left corner as I'm developing this, which frame am I on, just to make sure I'm doing the right thing at the right time. And back up in the main loop, this is the code here that ends up putting that frame number up in the upper left. So we just initialize U with the location in the current screen buffer we're writing to, and position it right where we want the numbers to go. I have a global variable progress counter that just increments each time through the loop, and that tells us what frame number we're at or which iteration we're at. And then I go to my scoring routine, which just dutifully takes whatever's on D and sticks it up on the screen. Obviously, at some point, I'm going to actually have to put scores on the screen, but for now, this is useful. So let's talk about those holes. Let's talk about how they get drawn. The main variable to keep track of the holes is this array. So this is just an array of 6 1-byte offsets. Each offset tells us where that particular hole is supposed to be on the screen. The length of this array determines how many holes I can have on screen at the same time. So I just picked 6 because that seemed like a good maximum number of holes that I would ever want on the screen at the same time. In fact, I think 6 is probably more than I would ever need. There's some more state I need in addition to this, but I'll get to that later. Each time through the main loop, we look at the level progress, we take our counter, increment it, and then use it to index into that array of level actions. I have an action jump table, which for now is very lonely. It only has one action. And the idea is that each of these will be an index into this table. And for now, we just have action hole, which indexes here to give us new hole. So whatever entry we indexed into, that's going to be the address of a routine, and we just jump to it. So new hole is responsible for going through that array, that global array of hole offsets, and finding the first one that's unused. This is kind of like some rudimentary memory management, where within that array it might be a little fragmented. Sometimes entries will come and go, and we might need to just find something that's not at the beginning and not at the end. So we just scan through until we find an unused entry in that array, and we just initialize it to be 31. So 31 as a byte offset takes us to the right-hand side of the screen. And so any new hole that comes on board is going to have that initial offset. And that brings us to draw holes, which we saw gets called every time through the main loop. It's divided into 2 parts. The first part has us erasing the portion of the hole that would be left behind if I didn't erase it. So we have a hole, and what we're doing in order to draw this is we have a bunch of bytes that basically fill out this rectangle here. And so every frame, the hole moves to the left. And so we're naturally going to rewrite part of the old hole with the new hole. But the part on the right-hand side of the hole before it moved is not going to get overwritten because the new hole is shifted to the left. So I need to have specialized code that will take, say, this last byte here and turn that into ground. Meanwhile, the hole will then get rewritten, shifted left by a byte, and everything else gets scrolled normally. But that's not quite right, because we're double buffering. So in any given buffer, it's going to appear like the hole has moved to the left by 2 bytes, because we keep alternating which buffer we write to and which buffer we show. So the buffer we're writing to doesn't have information that's 1 frame old. It has information that's 2 frames old. You might recall that I was dealing with a very similar problem regarding the car. So the car needs to slide left and right, and depending on how old the information is that a buffer has, one might need to be erasing information not from just 1 frame ago, but 2 frames ago. And the way I solved it is, for each buffer, I have this buffer info struct, and it just keeps track of where things have been drawn. so that when it's time to erase them, we know exactly where to go to erase it. So I've added to that struct a series of whole offsets. This is kind of like an analog to that global array of whole offsets that we already saw. But this isn't keeping track of the true state of the world. This is not the global state. This is just what's happening in this particular buffer and what has been written to it. Much like we have a global car lower right-hand corner variable, and that keeps track of where the car is right now. But this field from the buffer info struct tells us where we last drew the car in this buffer. So this completes the full state of the whole offsets. We've got the global array, and then we have this buffer local array that tells us what we drew in this buffer. And so that brings us back to the draw holes routine. Part 1 is this loop where we go through the buffer info local series of whole offsets, which is this, and we loop through them, calling this subroutine to erase the right-hand side of that particular hole. Now, in theory, I could just erase the entire hole. I could just replace it all with ground because I'm about to redraw the hole in its new location. But erasing the whole hole, takes more time than just erasing the portion of the hole that's not going to get overwritten anyway. So to save time, I'm trying to be a bit miserly with what I choose to draw onto the screen. On entry to the subroutine, the A register tells us the offset of the hole at the time that it was previously drawn. So it tells us where that hole in this buffer is right now, just before I'm about to shift it. I use that offset to adjust the X register to point to the exact part of the screen buffer where the left-hand side of the hole lives. And in the main case, this is what I do. I load up D with 2 bytes of solid red, and I store D into all these locations. This number here tells us which row we care about, so the holes happen to be 14 rows deep. And this +2 has me skipping from the left-hand side of the hole to just after the first 2 bytes of each row of the hole. So this basically points me right into the middle of the hole, so I can write 2 bytes starting there, and that will erase the right-hand half of the hole. That's the part of the hole that would not otherwise get overwritten when I draw the hole in its new location. I could use a loop to do this, but why not unwind it and get things a little faster? But of course, there are some boundary cases to deal with. If that hole's previous offset were -3, then that means that the left portion of the hole was 3 bytes off screen. That would leave only 1 byte left that's on screen. And when I redraw the hole in its new location, I'm not going to redraw the hole in its new location. It's not going to be on the screen anymore. So I just have to erase that 1 byte wide line at that part. Similarly, on the right-hand side of the screen, if my offset is at 29, then that would just leave 1 byte wide of a hole on the right-hand side after it shifts over. So I have these 2 special cases to erase not the full 2 bytes after the hole, but the second of those 2 bytes after the hole, or the first of those 2 bytes after the hole. Oh my gosh, this is gross. But it gets grosser. After this erase loop, where I keep calling erase hole right-hand side for all of the previous positions of all of the holes from this buffer, then it comes time now to draw all of the current holes into this buffer. I go into my global array of all of the offsets of where the holes really do live right now. For each one, I draw it, I scroll it, I deal with the case where it scrolls away by blanking it out, and that's all. But what does it take to actually draw that hole? The draw hole routine assumes that the A register is telling us the current offset of the hole that I'm trying to draw. It loads up X with the data of the hole. So these are the bytes that I'm going to be drawing. And this is thanks to my high school self who did all of that great artwork. I point U into my off-screen buffer and I position it using A as the offset, so I get my U pointer ready to draw everything. And in the main case, I have this slightly unwound loop, and it takes care of 1, 2 rows at a time. It uses the D register as a kind of gopher, so I read 2 bytes from my artwork buffer, store them onto the screen, read another 2 bytes, store them onto the screen, read another 2 bytes, next row, read another 2 bytes, that same next row. Then I update my screen pointer, I update my source buffer, I have a loop terminating condition, and then I go back up. Since holes happen to be 14 lines tall, and I'm doing 2 rows at a time, this should iterate 7 times. And if this is all there was, what's so gross about this? This is fine. This is beautiful. But of course, there's all this junk that I skipped over. Oh, yuck! What if the hole is all the way on the right side, just starting to creep onto the screen? What if it's a couple bytes onto the right side, still creeping onto the screen? What if it's three bytes in, but there's still 1 byte not there? And what about when it's scrolling off the screen? What if I need to draw just 1 byte on the right? Or what if I need to draw 2? Or what if I just need to draw 3? Oh my gosh! I have all these other variants of the loop. This one just draws 1 byte on each row. This just draws 2 on each row. This just draws 3 on each row. Yuck! And then what about the right-hand side? Just 1 byte. Just 2 bytes. Just 3 bytes. Blech! Anyway, it works. And as you can guess, I got all of this right perfectly on the first try. 'Cause I am just that good. And that just leaves one small, itsy-bitsy, humongous problem. As you may recall, the way my gravel moves is I just have a loop to scroll it. Whatever was here, I draw here. Whatever was here, I draw here. Whatever was here, I draw here. I just shift everything to the left. And really, I'm rotating rather than scrolling because whatever was at the very left, I redraw here at the right. But what happens when the hole is at the left? If I did that, I would suddenly get a hole here. And in fact, this was my grand master plan back when I was in high school. When I got the holes working there, I just drew 1 hole and it just kept coming on the screen, going off, coming back on, going back off. I just drew it as part of the ground, and that was my hole. And I knew that wouldn't be good enough, but I hadn't really gotten around to doing anything further with it. So here I had to figure something out, because as I scroll off, I do not want it to scroll back on. Instead, as it scrolls off, I just have some more magical gravel coming from somewhere and making its way onto the screen. And then eventually, I get a new hole to play with. Here he is. Oh, there's another one. Hello, holes. And then they scroll off. So the big change that I did to get that working is that last bit of that rotation loop where I took whatever was on the left of the gravel and stuck it on the right had to be replaced with me somehow feeding the right-hand side from a buffer of gravel. So here is that rotate ground top code now. As before, whatever was at offset 2 becomes offset 0. What was at offset 4 becomes offset 2. What was at offset 6 becomes offset 4. What was at offset 8? So this is me just copying everything 2 bytes to the left. But you'll notice I am no longer remembering what was at the leftmost byte. I clobber it right out of the gate without keeping track of what it was. So what do I stick at the right-hand side? After I take what was at offset 30 and move it to offset 28, I gotta fill something in over here. So I now have some more state that keeps track for this buffer where its gravel pointer lives. I follow that pointer to grab those 2 bytes. They are who get stored on the right-hand side of the gravel. I do some checking to see if I've hit the end of my gravel buffer, and then I update my gravel pointer. Seems simple enough, but getting this right was the hardest part of this whole portion of the game. And the reason is because doing double buffering just complicates everything. Let's take a closer look at the data. So back to the buffer info that we have 1 of these per buffer, so there's 2 copies total. We already talked about how we keep track of where the car was last drawn. We talked about where the holes were last drawn. There's 3 more fields that I added for this portion. This tells me where my current gravel pointer lives. This tells me where in my artwork buffer to grab the next 2 bytes of the gravel. And this tells me where my buffer starts and where my buffer ends. And here is the artwork buffer. I just grabbed this from the artwork I had already made using BASIC. I already had 2 versions of this because of the way I'm doing stack blasting now. And although I'm not doing stack blasting with the gravel anymore, since I already had it drawn, I'm just including them so I have a nice huge buffer of gravel. This way you don't really see the looping as obviously. And I have some freaking weird nonsense on either end. These are just 3 more bytes that are perfectly reasonable gravel bytes. Why do I do that? Let's take a look at how this is used to initialize the buffer infos. At the very top of the main loop, I've got a bunch of code that initializes the state of everything. And I have a nice chunk of code just to initialize the gravel. The start of the gravel feeder buffer makes perfect sense when we're talking about the first off-screen buffer. I just take the beginning of my gravel data, and that becomes where the gravel start is for the first buffer. If we skip down here to the second off-screen buffer, it starts its gravel buffer 1 byte in. So 1 byte after the start of the buffer is where the second off-screen buffer believes that the gravel starts. Similarly, in the first off-screen buffer, it thinks that the gravel ends 1 byte sooner than it really does. But in the second off-screen buffer, it thinks the gravel ends where it really does end. So the first off-screen buffer goes from here through this byte, through 30. The second off-screen buffer starts here at the very first byte of this and ends right here. And you'll see that these 2 bytes are the same. What I had to do was ensure that I had an odd number of bytes of gravel. Each of these has an even number. So when we add these together, we've got an even number. Then when I add these 3, it's now an odd number. And I just had to have the 2 off-screen buffers staggered by 1 byte. So whereas the first one goes here to here, the second one goes from here through here. And say as the second one is just about done with this, the first one is ready to pick it up where that left off. Oh my gosh, how many iterations of this that I went through before I got this to be this smooth. The gravel looked just awful until I got it just right. This is certainly the result of thinking, trial, error, thinking, trial, error, thinking, trial, error. And that's not all of the complication, because I didn't talk about how I initialize gravel cur, the current gravel pointer for each buffer. For the first off-screen buffer, gravel cur starts 32 bytes into it. And for the second off-screen buffer, the gravel pointer starts 33 bytes into it. What? Why don't the curs just start at 0? And I guess this would have to be 1 because it's supposed to be staggered and the second off-screen buffer should be after the first. But why are they starting in the middle? Well, the reason they're starting in the middle is because I do have to bootstrap this whole thing. I have to have a full screen's worth of drawing on screen when we first start. So I'm going to have 32 bytes of gravel already on the screen before we even start scrolling. So this ends up pointing us after those first 32 bytes, and this points us after the first 32 bytes of the off-screen of the second off-screen buffer. Oh my gosh! Why is this so hard? And this is all so that the simple feature of moving gravel that no one will ever notice or care about looks smooth. A lot of effort for what might not be considered much useful gain. The good news is that I got all of this working with absolutely no issues whatsoever, except for just a few minor mistakes. Anywhoozits, that's all for now. Thanks for watching.